I'm going to leave it as n, all right? So I've cut this number line into n pieces. What I'm going to do now is label these points. So this first point I'm going to call x sub 0. It's my 0th x point. This next point I'm going to call x sub 1. The next point I'm going to call x sub 2. Next one x sub 3, and so on and so forth. All the way down till I get to my last one, which will be my nth one. You with me? Oh, I did. Ah, you're watching. There. Because I wanted to confuse you. All right. Y'all got it? Now, what I'm going to do is I'm going to get another list of points. This list of, and you just have to believe this is going to lead us to where we need to go, right? Don't ask me why I'm going to do what I'm about to do, but in between x sub 0 and x sub 1, I'm going to pick a point. And that point, I'm going to call C1. And then I'm going to pick a point between these two, and I'm going to call that C2. Understand? And I'm going to do that the whole way through. And so when I get to this last little piece, right here, and I pick that last one right here, that's going to be Cn. Got it? Next thing I'm going to do, this is my function f, I'm going to take this C1, I'm going to plug it into my function. When you plug a number into a function, it spits out a number, doesn't it? But visually what's happening is when I plug in C1, I'll do it in red. When I plug in C1, I go up to the function somewhere and I'm landing on that point, right? Somewhere up there? And then from that point, I'm going to draw a rectangle to the left and down, and to the right and down. Now I need to zoom in on that a little bit so you can see it. Okay. A, which is x0, I'm going to say this is x1. I picked a point in there, C1. I went up to the function, and then I drew a rectangle that goes like this, and goes like that. Can you tell me the area of that rectangle? Okay, how wide is it? How wide's that rectangle?
C1 plus x1.
Say it again?
C1 plus x1?
No, the whole rectangle.
Oh, it's x1.
x1 minus x0. It's the difference between the x coordinates. Like if this was the number 3 and this was the number 5, then the distance between those would be 2, right? So the width of this rectangle, the width of that rectangle is x1 minus x0. You agree? That's how wide it is? How tall is it? F, close, f of, what, where did I go? I took the C1, I went up, right? And that's how high it is? F of C1? This would be equal to the area of my first rectangle, right? And then what I could do is do it again for the next point. So I go to C2, I go up here, I draw a rectangle out to the left, out to the right, I draw it down like that, right? Do y'all see it? Over here on this picture, I would have like C2 here. I would go up. I would draw out to the left, down. Draw out to the right, x2. Do you see that these rectangles are an approximation to the area, that I have error in there, just like the Chinese had error when they were doing their method of exhaustion, right? I'm going to have mistakes here. I've got error in here. I've got error right here, error here. So I'm going to be off, right? I'm going to be off. Can you tell me by looking at this what the formula for the next rectangle will be? F of c sub 2, x sub 2 minus x sub 1. That's the area of the second rectangle. And I continue this, right? And I keep doing this until I get all the way out to the last rectangle, right? Which would be f of c sub n, x sub n minus, what would be the one right before it? X sub n minus 1, good. And that would be the area of the nth rectangle. Yeah? Now, I said n is the number of rectangles I'm going to have. If I only use 2 rectangles, my estimate's going to suck, isn't it? Imagine that I have this graph. I don't want to erase that yet. Imagine I have this graph, and I only use 2 rectangles. The amount of error I'm going to have in there is a lot worse than if I had 4 rectangles, right? If I have 4 rectangles, my error becomes smaller. If I have 100 rectangles, my error becomes even smaller, right? 1,000 rectangles even smaller. So every time I let n get bigger, don't these rectangles get narrow, more narrow, narrower, skinnier, whatever, more narrower? Let's use that because I know that's wrong. Okay, the most narrowest. Okay, right. So as n gets bigger, these get narrow, 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 right? And what I'm going to do, or what Newton was doing with the calculus, actually Riemann is the mathematician who really came up with this, I'm going to let the number of rectangles go to infinity. That's what we're going to do. And if we do that, we should go to the true area. That limit should give us the true area. But look, I've got to add all these areas up, don't I? I don't want to add all those areas up. So now here comes the grand finale here. We're getting close to it. All right, we're getting close to it. I erased something up here just a second ago. It said f of c times b minus a equals capital F of b minus capital F of a. That came from the mean value theorem, didn't it? And I told you to remember something. I told you to remember that a and b were the 2 endpoints of the interval, right? And I told you to remember that c was inside of there. Take a look at this first area. What's x1 and x0? Isn't that the endpoint of this little interval right here? Is C1 inside of there? Yeah. Yes. That means the area formula for the first rectangle can be rewritten as what? What's the area of the first rectangle? I'm ready to erase this. The area of the first rectangle, this is what I'm going to try and do right now. I'm going to try and add up all the areas. Would you agree that that should be approximately the true area? I'm going to be off a little bit, right? But that should be approximately the true area. And the first area here, rewritten using this formula, should be what? This right here should be what? Come on, you can do it. Capital F of x1 minus capital F of x naught. We say x naught, but x sub 0 is fine. Do you agree that's the first area? According to the mean value theorem, that's what it is. Now, what's capital F? Hold on. What's capital F? If f was this function, right? What's capital F? It's antiderivative, right? So to find the area of the first rectangle, I can use its antiderivative. Let's keep going. What's the area of the second one? I'm waiting for that moment. I know some of you are already asleep, but I'm waiting for that moment where you're like, whoa, okay? Because it might happen here. What's the area of the second rectangle? So I say plus capital F of what? x sub 2 minus capital F of x sub 1. Give me the next one. Capital F of x sub 3 minus capital F of x sub 2. Wait a minute. 3, the third one. Yeah?
Yeah.
This is right.
It's got to be the next one minus the previous.
X sub 1, x sub 0, x sub 2, x sub 1, x sub 3, x sub 2. And this would keep happening, right? And I would keep doing this all the way till I get to the very last rectangle, which would be capital F of x sub n minus capital F of x sub n minus 1. Do y'all follow me? We're almost there. We're almost there. We're almost there. I'm going to break these up a little bit here. Ah, you see it? Yes, you see it. Good. So if I break these up into where they came from, the individual rectangles, you'll notice that in every single pair that we have here, the first guy or girl, whatever you want to look at it, the first one here will always get killed off by the second one in the next pair over. Right? Those two kill each other off. The first one here gets killed off by the second one over there. The first one here gets killed off by the second one in here somewhere. So that one's gone, right? The first one here gets, oh wait, there is nothing out there, right? Right, if I stop here, if I stop at n, then there is nothing over here for this one to get killed off by. So this one's still here, isn't it? Now what about this one? Does this one get killed off? Yes. By what? The one before it, right? The one before it killed that one off. So what's still here? Capital F of x sub n and capital F of x sub 0. But what was x sub 0? Go back to the picture. Wasn't it A? It was the first endpoint. And what was x sub n? The last endpoint, B. So that means that the area of the area underneath that curve F is just capital F of B minus capital F of A. Now, it's an approximation. How do I let my approximation get better? I let the number of rectangles go to infinity. That's what I do. So this was a sum, wasn't it? This is a sum of things. And if I let n go to infinity, it becomes an infinite sum, doesn't it? So the technical way of writing this, and I don't want to get bogged down on this, but right here, if I wanted to write this technically, I would write it like this. Sum n equals 1 to infinity of f of c sub n, sorry. I n I x sub I minus x sub I minus 1. That would be the technical way of me saying to add up the first n rectangles. So if you've never seen this symbol before, that's a sigma, Greek S, capital S, which stands for summation. And what we're going to do is we're going to start with I being 1. If I replace this with 1, 1, and 1, I would get this. That's what I would get if I plugged in 1 right here. Then I'd say plus. Now I let n go to 2 and do the same thing. So I add to this f of c sub 2, x sub 2 minus x sub 1. Then I let it go to 3, then 4, and I stop when I get to n. It's not important that you understand all the mechanics of that notation. But that right there adds up the first n rectangles. And then what I do is out here I take the limit as n goes to infinity. And that gives you the true area. That's the true area underneath that curve. And so since this true area is this very fancy summation that you're going to let become infinite, we're going to have a special kind of notation we're going to use. And here's what it is. Instead of writing all this, I'm going to write this, which is just an S stretched out. And instead of writing f of c sub I, I'm just going to write, well, wait a minute. Wasn't this just the height of the function? Wasn't that the height of the function? And that's just the function's value at some x. And then this right here, this was the little width of the rectangles, right? It's the change that we have in x. And we're going to call that dx, which is a little infinitesimal change in x. That's the notation for this summation right there. And it turns out that at the end of the day, that if you want to know the area, well, let me do it on the next line. I just want to show you where the notation comes from, okay? This symbol and this dx come from this formula. But now, the evaluation theorem, the end result, and then we're going to do an example. This is amazing, isn't it?
Was it an example?
No, this is not an example. This is just showing you the theorem I'm about to give you.
So this is the proof?
This is almost the proof. It's a loose proof. It's definitely not rigorous enough for a true math person, but for introducing someone to the idea, I need to show you something you can follow, right? I hope you could follow that. If you didn't, then. Okay, so evaluation theorem. That was all the development of it, but here's the end result. The net area under a function f on a closed interval AB is what? What did we just say? Capital F of B minus capital F of A. Now, the better way to write this using the notation of integration is this. This right here is the notation we use. So I'm going to point out the main difference in this notation from the notation we've done before. Notice that I put something here and here. Before, those things weren't there, right? Those things weren't there before. But now, if we actually put something here, which they're going to be numbers, then our answer is the area under the curve.
I've seen that before.
Yeah?
Numbers.
Yeah. This is the evaluation theorem right here. It's amazing. To know the area underneath the curve, all you need to do is figure out the antiderivative of the function. And then just evaluate it at the two endpoints. That's all you need. What?
I just didn't know what it was at the time.
Yeah. All right, so let's do now, finally, something you would see on the test. Example. Find the area under f of x equals x plus 1 on the interval 0, 3. Bless you. So someone tell me what I have to do. In order to answer this, what do I have to do? Actually, I don't need a picture at all. I could just, to have it. I just need the antiderivative. That's all I need, right? That's all I need. If I have the antiderivative, I'm going to get the answer. So let's use the proper notation to write this down now. The proper notation would be, I want to know the antiderivative of x plus 1 with respect to x, and I'm looking between 0 and 3. Notice the lower part here, this right here, is the number on the left side, and this is the number on the right. We actually have technical names for these. This is called the lower limit of integration. And what do you think the one up there is called?
The upper.
Yes. The upper limit of integration. Right? So we have, hey, what's up? You're late. You're late. You can have a seat. I've never seen her before. So we have the lower limit of integration, the upper limit of integration. But all I need is the antiderivative, right? So the way that we actually write this out to make our lives easier is this. What we do first is we say this is equal to, let's just find the antiderivative. Okay? So what is the antiderivative of x plus 1?
X squared.
1/2 x squared
Plus
plus x plus c. Now you're going to see in a little while that c is not going to matter. All right? But do you all agree that's the antiderivative? But I'm not done because I actually need to plug in the two endpoints into that, right? So the notation we use now is we put a bar over here to the right of this. We put 0 down here and a 3 up here. And that's just the notation we use to remind us now we need to plug 3 into this, plug 0 into this, and subtract the 2. All right? So now my next line, or next as I continue my equals, let's first plug 3 in. So this right here is going to be, this part right here is the f of b minus f of a. And b for us is 3, right? So plug 3 into this, and what do you get? 3 into that. I'm going to say 9/2, right? Plus 3 plus c, right? Now I plug in a, but a is 0. So what happens if you plug in 0 to this? You just get c. And now let's subtract them. What happens to those c's? They're gone, aren't they? Aren't they? So I'm going to have 9/2 plus 3. Let's get a common denominator. 6/2 added up. 15/2 is the area.
Is there?
Was that-
Is there dimensions?
Oh, good question. Are there dimensions is the question. If we had the unit of measure like feet or whatever, then we'd say like square feet, or if it was miles, we'd say square miles. But this is a unitless number. Someone would have to provide me the actual.
And since they're not,
Well, this is actually, the reason I gave you this example is because now I want to draw it. I just want to show you this curve real quick. Isn't that a line?
yeah.
And it's moved up 1. So it would start here at 1, 1, and then it would go, what, up 1 over 1? Up 1 over 1, up 1 over 1 like that. And that would go till 3. So at 3, how high is it? 4? 3, it's at 4. We're trying to find the area below this. So I'm trying to find this area right here. I'm going to check my work right now to see if we got it right. So if I were to ask you to find the area of that, you could break it into first a rectangle right here. What's the area of that rectangle right in here? That's 3. I bet you that's 9/2. Let's see, is it? What's the, if you just look at that little triangle there, what's the base? 3, what's the height? You're going from here to here, right? So from 1 to 4, that's 3. 1/2 base times height, 9/2. 3 plus 9/2, 15/2. Worked. Yeah? That was just to verify the formula works. It's not an interesting problem because it's straight lines.
Good question.
Yes.
This only measures underneath up until the x.
X-axis. Yes, below to the x-axis. Now in Cal 2, you will start to do things like if you have a function up here and a function down here, two separate functions, you know, what's the area between them? We'll be able to handle that. Just, this is the beginning. Well, if it's different functions, those look like they were symmetric, but. Okay, so how about this? What if I change this problem to x squared plus 1? The antiderivative is going to change. That's it, right? I'm still going to plug things in. But this is no longer a straight line. This is now a parabola, isn't it? And because of that, the area is going to be different, but it's curved. And you cannot do this any other way than to use the integral. So let's try this one. Yes, the c's are always going to cancel, which is why I'm about to do something a little different. So this means I want to go integral from 0 to 3, x squared plus 1 dx. So what I do first is I find the antiderivative. 1/3 x cubed plus x. But instead of writing plus c here, I'm not going to write it at all, because I know it's going to cancel, always. Right? It's always going to go away. And then I'm going to write this little bar over here. Put 0 down here, 3 here. And then I'm going to write, I like to always put two sets of parentheses. That's just my habit. First I plug in 3.
You didn't put the c there.
I did not put the c, because I said, I know that if I put the c, it's going to cancel because it's going to be here and here. They're going to subtract and it's gone. So when you're doing these areas, you don't have to put plus c. So what happens when I plug in 3? Get 9 plus 3? Right, this is 27 divided by 3 is 9 plus 3. And then when you plug in 0, you get 0. And so that's just 12. That's an interesting area that you get 12 for that, but that's what you get.
Almost too nice.
Yeah, it seems too nice. Remember, that's saying if you graph this parabola that's been moved up 1, and you look between 0 and 3, and you want to know what that area is, it's actually exactly 12. Doesn't seem like it should be that way, but it is. So now if I tell you that these problems, I'm going to put a couple of these on the test. Is this, you think this is doable?
As long as you get the notation down.
Okay.
I guess as long as the antiderivative is not
I think we can do one last one before we call it. I want the antiderivative, or sorry, the area under the sine curve between 0 and 2 pi. Forgot to close this off. So when I set this up, integral 0, 2 pi here, sine x here, dx. What's the antiderivative of sine? Be careful. Negative cosine, good. Negative cosine x. A bar here, 0 to 2 pi, equals two things subtracted. First plug in 2 pi. So what is cosine of 2 pi? 1. Cosine of 2 pi is 1. So it's actually -1, isn't it? All right. Minus, over here, what's cosine of 0? Also 1, but it's minus. So another -1. And so you get -1 plus 1. Right? Negative and negative is positive. Which is? What? That doesn't seem right.
Well, it cancels each other out.
Ah, the sine curve between 0 and 2 pi looks like that. And this area up here, it must be counting that as positive, and it must be counting this area down here as negative, and they must be offsetting each other and getting 0, which is the way it works. So I said earlier that it gives you the net area. What I mean by that is anything above the x-axis is counted as positive, anything below the x-axis is counted as negative. So you have to be a little careful with this.
It won't take the first.
Pardon?
It won't take the first.
That's right. So how could I figure out the total area?
You would have to change the interval.
Go to pi instead, right? Go from 0 to pi and double that answer, and that would give me the true area here. So how would this change if I went from 0 to pi instead? This would change, right? How would that go? What's cosine of pi? No. -1, but then it's negative. So this is +1, right? And if I plug in 0, we already did that, right? That came out to be -1 here. Now you're going to have 1 plus 1, which is going to give you 2. So if you've ever sat there and looked at the sine curve, just been like, hey, I wonder what the area under that first arc is. Well, guess what? It's 2. That's the area under there. Just 2 whatevers. Yeah, so like if this was feet here, you know, feet, you're measuring in feet, then that would, the area would be square feet. I want to write the final version of the evaluation theorem. Net area under F on AB is given to you by this notation. There. The only thing I did here that's different than what I showed you earlier is I included this intermediate step, which is where you actually find the antiderivative and then draw the bar. But if I would have put that up there to begin with, you would have been like, what the heck is this? Right now you understand what that part of it is?
I guess that comes in handy if the antiderivative is kind of complex.
Yes, you always want to write it down first. So it's like, okay, I'm gonna find the antiderivative first, figure out what that is, and then I'm going to go ahead and plug in the numbers. The finding of the antiderivative is the part that will be challenging later. You like? You like?
It's actually kind of cool.
So I'm going to show you one thing. I still have 5 minutes. I want you to get your money worth. 5 minutes, okay?
We're not going to get any service?
You can start putting your books away though, and you can start turning off. But I want to show you something. This will help you later for you Cal 2 people, which is most of you, right? If you are talking about the area underneath that curve, and you look at this as being an infinite sum, right? This was an infinite sum. This was the height of the rectangle, and this was the width of the rectangle, right? So this is just saying, hey, look, I'm going to take that function, and I'm going to add up an infinite number of rectangles where this is the height and this is the width, right? Yeah? Okay. Now, what if I want you to take a function and I want you to wrap it around the x-axis, three-dimensionally? Imagine taking this off the piece of paper and wrapping it around. You would create a solid that would look something like that. Do y'all see it? Do y'all kind of see that solid?
Yeah.
Kind of?
All the engineering stuff.
Do you kind of see the solid? I mean, yeah, if I just take my phone and I start wrapping it around the x-axis like that, then I would make this solid cylinder, wouldn't I? If here's the axis, So I wrapped it around. My phone used to be in here like that. Wrapped around, I got this solid thing, right? Got it? Now, what I'm going to do now is come up with the formula. I'm going to figure out what the volume of this is. And the way to do it is I'm going to take just look at one of those rectangles. What if I took one of those rectangles from over here and wrapped it around the x-axis? Just one of them. If I wrapped it, it would look like this, wouldn't it? And this right here is really a cylinder. What's the volume of a cylinder? If you look it up, pi r squared h, right? Now it's sideways, so let me draw it this way for you. What is the height of this little cylinder? Well, it's that piece, right? Which was this, which in this formula is dx, right? So this is dx. Okay, what is the radius? What is the radius of this cylinder? Well, that's this, right? Which is this, right? So isn't this radius just f of x? So what is the little volume of this piece right here? Just of that little piece? Pi times r squared, which is f of x squared dx. So guess what? If I want to know the volume of this, I know I'm almost out of time. Let's say I were to take f of x equals x plus 1. Remember that one we did on 0, 3? And then this time, instead of me asking you what the area below it is, if I asked you to wrap it around the x-axis and give me the volume, here's what you would do. Integral 0 to 3. Integral's telling you, look, I'm about to add up a bunch of shit right now, like a bunch of it, right? Now what am I going to add up? A bunch of volumes, a bunch of cylinders. And each cylinder has this formula. So this integral is going to have pi, the function squared, what? dx. That's it. That right there will give you the volume of that graph wrapped around the x-axis. So I would pull the pi out. I would expand this, square it. I have no time. Pi 1/3 x cubed plus x squared plus x. I'd evaluate that from 0 to 3. So I integrated each one of those term by term. I kept the pi out there. I plug in 3, I plug in 0, subtract. That's the volume. That's it. That graph wrapped around the x-axis would look like this. If you get the idea. And that's what you do in applications. You can wrap it around the x-axis, y-axis, and a bunch of other stuff. So, all right. I guess I'll see you Thursday, everyone. Have a great weekend.
You do that a lot with CAD.
What's that?